Mastering Tail Latency, Unmasking and Mitigating P99 Spikes. Hello, and welcome back to the System DR podcast. Today, we're tackling a silent killer in system design, something that makes your fast system frustrating for users even when all your dashboards look green. As a principal engineer, I've seen this play out countless times. Systems with impressive average response times, yet user complaints flood in. It's so slow, or it just hangs. This isn't a minor bug. It's a fundamental misunderstanding of what performance truly means at scale. We're going to pull back the curtain on this deception and arm you with the tools to build truly resilient systems. Most folks instinctively reach for the average when talking about speed. My service responds in 100 milliseconds on average. Sounds good, right? But averages, my friends, are liars. Imagine a massive e-commerce platform. 99% of your users complete their checkout in a snappy 50 milliseconds. Fantastic! But 1% are stuck staring at a loading spinner for 5 full seconds. Your average might still look amazing, but that 1% represents thousands, even millions of frustrated customers. These are the users who abandon their carts, leave bad reviews, and never come back. This is why in high-stakes production environments, we absolutely do not trust averages. This is where percentiles become your best friend. They paint a much more honest picture of user experience. P50, or median latency, tells you that 50% of your requests are faster than this value. It's the typical experience, a good baseline. P90, latency means 90% of your requests are faster. This gives you a sense of how the majority of your users are doing. But the big one, the one we obsess over in FANG companies, is P99 latency. This means 99% of your requests are faster than this value. The P99 is the tail of your latency distribution, and it's where the most frustrating, often hidden user experiences live. When this number spikes, it's a blaring siren indicating a significant problem for a non-trivial segment of your user base. P99 latency spike is when this value suddenly shoots up, even if your P50 and P90 remain stable. It's a critical early warning sign that something is fundamentally wrong for your most unlucky users. So what causes these spikes? In complex distributed systems, it's rarely a single obvious thing. These are often the second-order effects of architectural choices or subtle resource contention. Let's look at some common, non-obvious culprits. First, garbage collection pauses. In languages like Java or Python, the runtime occasionally pauses the application to clean up memory. While usually quick, a stop-the-world GC pause can hit a few unlucky requests hard, making them wait significantly longer. Imagine a traffic cop suddenly stopping all cars on a freeway for a few seconds. Most cars are fine, but those directly in the path experience a significant delay. Then there's resource contention. This is a classic. A few requests might get stuck waiting for a shared resource, perhaps a database connection from a limited pool, a lock on a critical data structure, or even a thread from an overloaded thread pool. These aren't always deadlocks, but rather slow locks that delay specific requests while others sail through. Queuing delays are another one. A sudden brief burst of traffic can overwhelm a service, causing requests to pile up in an internal queue. While the system might recover quickly, those requests at the very back of the queue experience much higher latency, even if the average queue time is low. And finally, I/O or disk slowness. Ever heard of a cold cache? A request might hit data that isn't in memory and has to be fetched from a much slower disk or network storage. While most data is hot and fast, that rare cold read can introduce a significant, unpredictable delay for a few requests. Today, we'll simulate a resource contention issue by intentionally slowing down a small percentage of requests to clearly show how even a tiny fraction of slow requests can dramatically inflate your P99 metric. Now, why does this matter so profoundly in distributed systems? Think about the fan-out problem. In a modern microservice architecture, a single user action, like loading a social media feed, might fan out to a dozen or more backend services. If each of those services has even a tiny P99 issue, say 1% of its requests are slow, the cumulative probability of the overall user request hitting at least one slow dependency skyrockets. This is a crucial, non-obvious architectural trade-off. What looks like acceptable latency in a single service can become a catastrophic user experience when composed in a distributed system. This is why in production we don't just monitor averages. We deploy sophisticated monitoring tools to track P50, P90, and critically P99 latency for every single critical service and endpoint. These dashboards are our early warning system for systemic issues that averages would completely hide. To truly grasp this, we're going to build a simple yet powerful client-server system. Our goal is to create a controlled environment where we can introduce tail latency and observe its immediate, dramatic impact on the P99 metric. Our architecture will consist of two main parts. First, a load generator, our front-end client, a React.js application. This is our workhorse. It will hammer our backend with thousands of concurrent HTTP requests and, crucially, measure the response time for each one. Then it'll crunch those numbers to display our P50, P90, and P99 latencies. Second, a latency spiking service, our backend, a simple Python Flask web server. This service will have two key endpoints, /fast, which responds almost immediately, simulating a typical efficient operation, and /slow, which will intentionally introduce a significant delay, say 500 milliseconds. This is our controlled culprit that will generate the tail latency. Here's how the control and data flow. The front-end client kicks off a high volume of concurrent requests to the backend. For each request, the client makes a decision. Most of the time, say 99% of requests, it hits the fast endpoint, but for a small, controlled percentage, like 1%, it hits the slow endpoint. This is how we introduce our tail latency problem. The backend processes the request. If it's slow, it simulates a long-running task by pausing for 500 milliseconds before responding. The front end precisely records the time taken for each request from sending to receiving the response. Once all requests are complete, the front end calculates and displays the P50, P90, and P99 latencies on the UI. You'll see the P99 value dramatically higher than the others, clearly demonstrating the spike. This setup provides a crystal clear empirical demonstration of how a small number of slow requests can disproportionately affect the overall user experience, as revealed by the P99 metric. Observing the problem is just the first step. Fixing it is where the real engineering comes in. The core issue with a high P99 latency is that clients are often forced to wait indefinitely for a slow dependency. This isn't just bad for the user, it's a systemic risk. A client waiting for too long consumes resources, threads, memory, network connections, and if many clients get stuck, it can lead to cascading failures and even bring down the client application itself. This is where client-side timeouts become a critical production-ready pattern. Instead of passively waiting, the client actively decides how long it's willing to wait for a response. If the dependency doesn't respond within that window, the client cuts it off and moves on. This is where we use JavaScript's abort controller API to implement this timeout. Think of abort controller as a kill switch for your fetch requests. Why is this a game changer? First, resource conservation. It prevents client resources from being tied up by unresponsive services. Second, improved user experience. Rather than a frozen screen, the user gets a timeout error much faster, allowing for retry logic or graceful degradation. And third, cascading failure prevention. A slow upstream service won't block the downstream client, preventing a localized problem from becoming a system-wide outage. Here are the conceptual steps for the fix. You'll create an abort controller before each fetch call, giving you a unique signal for that specific request. Then you set a timeout using setTimeout to schedule controller.abort after your desired duration. This is your patience threshold. Next, you link it to fetch by passing the controller.signal into the fetch options. Now, the fetch request is listening for that abort signal. Crucially, you'll handle abort errors. In your try-catch block, specifically check for error.name equals abort error. This allows you to differentiate a timeout from other network errors and log it appropriately, perhaps recording a fixed timeout value like 100 milliseconds for latency calculations. And finally, a small but vital detail for robust, long-running applications: always use clear timeout in a finally block to prevent memory leaks from timers that are no longer needed. By implementing this client-side timeout, you're not just fixing a bug, you're building a more resilient system, one where a slow dependency doesn't unilaterally dictate